Bismillahirrahmanirrahim. Assalamu alaikum, students. This is our first lecture for your sixth semester course. I've already shared the syllabus copy, or you can easily download it from the website of Kashmir University. You know that our syllabus, our course is titled as Modern Physics Second, and it is a 4-credit course. That means in a way that in your question paper in theory, your marks will be maximum 60, right? You might have seen your syllabus. It consists of 4 units: unit first, unit second, unit third, and unit 4. Now, unit first and unit second is mostly, you can say, condensed metaphysics, and unit third and unit 4 is mainly semiconductor electronics. So today we will start our course. We will start with unit first, right? So I would introduce you to this course in today's lecture. So I'll write first introduction. What is condensed matter physics? If you ask this question, if you Google it, you will get the answer from Wikipedia as this. I quote Wikipedia. It says, condensed matter physics is the field of physics that deals with the macroscopic and microscopic physical properties of matter. In particular, It is concerned, it is concerned with the condensed phases, condensed phases that appear whenever the number of constituents in a system is extremely large, and the interactions between the constituents are strong. The most familiar, the most familiar examples of condensed phases are solids and liquids, which arise from the electromagnetic forces between atoms. Let us try to analyze this definition of condensed matter physics. So it is a field of physics. Physics has many fields, as you know. So condensed matter physics is one of its fields. It deals with what? Macroscopic and microscopic physical properties of matter. You know, matter has physical properties. Different matter shows different physical properties. So condensed matter physics deals with macroscopic as well as microscopic physical properties of matter. Macroscopic, you know, when you talk of the physical properties of matter as a whole, you're discussing macroscopic properties. Now, if you take the constituent particles of the matter into consideration, you consider the matter at microscopic level and discuss its physical properties in terms of its constituent particles. We are talking of microscopic properties, right? And in particular, it is concerned with condensed phases. You know, matter has many phases. You know, the solid phase, liquid phase, gaseous phase. There's a phase called plasma. There are many phases. We have, for example, helium. It exists as helium first, helium second. There are also phases. So we have many kinds of phases of matter. Condensed matter physics deals with condensed phases that appear when the number of constituents in a system is extremely large and the interactions between the constituents very strong. Now, the most familiar examples of condensed phases are solids and liquids. So when you deal with condensed matter physics, you are dealing with mainly studying or discussing the physical properties of solids and liquids both. You know, the electromagnetic forces exist between the constituents of solids and liquids. It is the electromagnetic force that binds atoms in liquids as well as solids. So condensed matter physics deals with the study of microscopic and macroscopic physical properties of solids and liquids both. Now the term condensed matter condensed matter is than more general than study of solids, but it because it considers the studying of liquids as well, right? This condensed matter term was promoted by Nobel laureate Philip Anderson. Philip W. Anderson, right? This condensed matter physics is by far the largest single subfield of physics. So we have physics that has a field called condensed matter physics, right? And under that, we have solid state physics. Solid state physics is a subfield of condensed matter physics. So condensed matter physics is more general. It contains the study of solids as well as the study of other condensed phases like liquids, right? Now, why do we study condensed matter physics on the first place? There are reasons for that. Some reasons we can list this way. One reason is it is the world around us. That means almost all of the physical world that we see is in fact condensed matter. You can ask questions like, why are metals shiny? And why do they feel cold. You can ask another question like, why is glass transparent? Or you could ask a question like, why is rubber stretchy and soft? All these questions come in the domain of condensed matter physics, right? Second reason can give, this was the first reason. Second reason to study condensed matter physics, we can say it is useful. You know, over the last century, our command of condensed matter physics has enabled us humans to do remarkable things. We have used our knowledge of physics to engineer new materials and exploit their properties to change our world and our society completely. Perhaps the most remarkable example is how our understanding of solids enabled new inventions exploiting semiconductor technology. You know, we have been able to construct computers, mobile phones, etc. Normally, we take these things, these electronic devices, which are at our disposal due to condensed matter physics. We can say we take having them as for granted, but it is through the study of condensed matter physics that we have been able to achieve such devices, right? And you can give another reason why we study. There can be many reasons. Another reason we can give why we study condensed matter, because it is a laboratory. Condensed matter physics is perhaps the best laboratory we have for studying quantum physics and statistical physics, right? You have gone through many concepts of quantum mechanics in your previous semesters, statistical mechanics, right? Now, these ideas of quantum mechanics and statistical mechanics are deeply grounded in condensed matter physics, right? These can be some good reasons for studying condensed matter physics. Then, why we separately study solid state physics? Simple answer to that is condensed matter physics is huge. So we take portion of condensed matter physics as solid state physics and study it separately as a course. So mainly our first two units are solid state physics. You can say it is only the portion of condensed matter physics, right? And semiconductor electronics is also in a way solid state physics because semiconductors exist in solid state. So when we deal with semiconductor electronics, sometimes we call it as solid state electronics also. This was a little introduction about this course. I hope you will not waste your time and you will work hard throughout the course. Now let us move to next topic. I will, you know those things. I am just trying to refresh your memory so that I can move forward. So my next heading is heat capacity and specific heat. You know these ideas, as I already said, I need them, so I'm refreshing them. How is defined heat capacity? Heat capacity is denoted by C. It is defined as the amount of heat energy needed to raise the temperature of a body by 1 degree. That is by definition the heat capacity of a body. I repeat, it is the amount of heat energy needed to raise the temperature of a body by 1 degree. So larger the heat capacity of the body, that means you require more heat to raise its temperature. That means in a way it is difficult to heat it up if its heat capacity is large. You know the historical unit of heat energy is calorie. And calorie by definition, you know, is the amount of heat energy needed to raise the temperature of 1 gram of water through 1 through 1 Celsius degree, right? You know these definitions, I am just repeating them. So calorie by definition is the amount of heat energy needed to raise the temperature of 1 gram of water through 1 Celsius degree, right? And you know this convergent relationship, you know, SI unit of heat or any kind of energy is joule, and the relation between calorie and joule is 1 calorie is 4.184 joule. This result is sometimes called the mechanical equivalence of heat. So this allows you to go from calorie to joule or joule to calorie, right? Now, heat capacity of an object is proportional to its mass. Larger the mass of a body, larger will be its heat capacity. The heat capacity per unit mass. The heat capacity per unit mass is called the specific heat. We use little c for it as a symbol. So heat capacity per unit mass is specific heat. So if C, small c is the heat capacity of, specific heat of a body, capital C is its heat capacity, m is mass, you can write small c equal to capital C over m. Small c is, let me label it, small c is specific heat, capital C is heat capacity of a body, m is mass of the body, right? We use another kinds of heat capacities also. The heat capacity per mole is called the molar heat capacity. I represent it by capital C prime. So you can write molar heat capacity equal to small c times m. Small c is specific heat, m is mass of 1 mole. Mass of 1 mole which is called molecular mass. So this is equation 6. So when you talk of molar heat capacity, your mass is 1 mole, right? When you talk of specific heat, your mass is 1 unit, 1 kg, right? The molar heat capacity is specific heat of a substance times its molar mass or molecular mass. It's mass of 1 mole of the substance. There is a relation Q equal to heat capacity times delta T. Q is here heat energy transferred into or out of a system right? Delta T is the change in temperature of the system. Heat capacity is the constant of proportionality. So heat required to change the temperature of a system is proportional to change in temperature. C is the constant of proportionality, which is heat capacity. You can write this relation as you can replace capital M by mass of the system under consideration times the specific heat into delta T. You simply use this equation 1. Capital C can be written as mass times small c. I name it equation 3rd. This is also important equation which we use. What is it? Q is equal to mc delta T. Q is the heat that is put in. If it is put into the system, change in temperature is positive because the temperature of the system will increase. Final temperature is greater than initial temperature. C is specific heat capacity of the system, M is mass of the system. This equation you can use in reverse also. You can take Q amount of heat out of the system. In that case, your delta T will be negative because temperature of the system will decrease. So keep this equation in mind also. You need it. Now, there's another idea. We can heat a system under different conditions. If we heat a system at constant pressure, we talk of Cp, this heat capacity at constant pressure, C subscript P. If we heat the system at constant volume, that means keeping its volume fixed, and we talk of Cv, that is heat capacity at constant volume, right? Now, in general, the amount of heat needed to raise the temperature of a body at constant pressure, which is heat capacity at constant pressure, is not the same as that heat needed at constant volume, that is Cv, heat capacity at constant volume. So in general, they are not the same. So we must distinguish therefore between Cp and Cv. Now, when you talk of capital Cp, you are talking of heat capacity at constant pressure. If you write small Cp, then you are specifying the mass as 1 kg or 1 gram. That means you are taking unit mass, then it is specific heat capacity at constant pressure. Similarly, you can talk of here small Cv as specific heat capacity at constant volume, right? Now, for solids and liquids, the difference between Cp and Cv amounts to a few percent or less and can be ignored except in the most precise experiments. But for gases, the difference between Cp and Cv is significant. You might be knowing this equation. For an ideal gas, we have the relation Cp is equal to Cv plus Nr. N is the number of moles, R is the universal gas constant. So for an ideal gas, Cp is greater than Cv by an amount Nr, right? There is another result which I want to present before you. The molar heat capacity, the molar heat capacity for all metals is about the same, about the same. Molar heat capacity for all metals is approximately 3 times universal gas constant R. This result, molar heat capacity of metals is approximately 3 times R, is called Dulong-Pettit law, right? This was a little introduction to the specific heat capacity, and other kinds of quantities which we use. I will give you a homework, simple question. The question says, when 100 gram of aluminium shot is heated to 100 degrees Celsius and placed in 500 gram of water, initially at 18.3 degree Celsius, the final equilibrium temperature of the mixture is 21.7 degree Celsius. What is the specific heat of aluminium? I repeat the question. When 100 gram of aluminium shot is heated to 100 degrees Celsius and placed in 500 gram of water, initially at 18.3 degrees Celsius, the final equilibrium temperature of the mixture is 21.7 degree Celsius. What is the specific heat of aluminium? This is your homework. Let me summarize this lecture a bit. So we started our course. We defined condensed metaphysics. Then we said solid state physics is part of it. So our 2 units, or in fact all the 4 units, are connected in a way with solid state physics, right? Then we gave some reasons to study condensed metaphysics, and we defined certain quantities like heat capacity, specific heat, calorie. We talked about molar heat capacity, talked about this equation, Q is equal to mc delta T. We talked about or differentiated two kinds of heat capacities, heat capacity at constant pressure and heat capacity at constant volume. We talked about Dulong-Pettit law, and I gave you this simple homework. So do this homework, don't waste your time, and do not forget to subscribe my channel. Thank you. God bless you. Assalamu alaikum.